All right, so we were looking at carbohydrates, and there are a few disaccharides which you need to know. You can draw the structures if you know the structure of glucose and just a few others. So most of them are about glucose and fructose. So one of them that we did was maltose. And maltose is glucose alpha 1,4 glucose. So this is what should tell you everything about the structure of the disaccharide maltose. What it says is the carbon 1 of this glucose is linked to carbon 4 of this glucose, which means this is the reducing end. This still has a anomeric OH. So if you draw the structures, it will be like this. So this is linked alpha 1,4. So alpha means down, and 4 at this carbon. So this is glucose, and the structure of glucose is easy. They're just going up and down alternately. So another one is also glucose, and it is at the 4th carbon, so that means it is this carbon. So that will also have the OHs, which I'm not writing. But the important thing is that this glucose will always be alpha because it is a glycosidic bond. So a glycosidic bond doesn't go back and forth between the linear and the ring chain. Once it is formed, it stays as alpha. And the other anomeric carbon is on this glucose, which can be up or down. So you will always have this ring converting to the linear form and then ring again, and every time it does that, it will give you a mixture of alpha and beta. Whereas this ring will not open up, it will not become linear, it will stay like this because this is a glycosidic bond which does not go back and forth. So once again, this is called the reducing end because this is the anomeric OH, which is a reducing agent. So it is called the reducing end, and this end is the non-reducing end. And in the same way, if you have multiple units to make a polysaccharide, at one end will be the reducing end, and the other end will be the non-reducing end. If you have branches, then for every branch you are increasing the number of non-reducing end, but the reducing end stays the same. So there will be one reducing end and multiple non-reducing ends. Starch, as I said, contains amylose and amylopectin. Amylopectin has branches, alpha 1,6 branches, and when you digest starch, that will give you maltose as the end product. And at the branches, it will be alpha 1,6 branches, so it also gives you isomaltose as the end product. So isomaltose is glucose alpha 1,6 glucose. So this ring, instead of joining to carbon 4, it will be joined to carbon 6. So you draw the other ring like this, joined to carbon 6. So that will be isomaltose. Another name that you should know, it's biologically relevant or relevant in humans, is lactose. And lactose is galactose beta 1,4 glucose. Galactose beta 1,4 glucose, which once again means that this ring is always present as the beta structure, it doesn't open up to become the linear chain. This is the one that open up to give you the linear chain, and then again the ring, and that gives you a mixture of alpha and beta. So this is the reducing end, this is the non-reducing end. So lactose, as you know, is milk sugar. It is a disaccharide of galactose and glucose. And another, of course, biologically relevant sugar, which is most common, not really made in humans, but we consume a lot of that, and that is sucrose. So sucrose has a different type of structure. So it is alpha D glucopyranosyl. As I said before, all these are abbreviated names. The actual name will again be alpha D glucopyranosyl. These are 6-membered rings for both of them, which is usually not written, but that is part of the name, alpha D glucopyranosyl or beta D glucopyranosyl. So for sucrose, it is written because the next one is a fructose, and fructose is a 5-membered ring. So one is a 6-membered ring, another is a 5-membered ring. That's why it is usually written as alpha D glucopyranosyl. And then this is a beta 1,2. Actually, the beta is written here. So beta D fructofuranoside. So that's a long name. One is 6-membered, fructose is 5-membered, and that's called a furanose. And look at the name here, it is furanoside, which means this is also a glycosidic linkage. So the fructose doesn't have its anomeric OH. It is involved between the carbon 1 of this. Remember, carbon 1 is the anomeric carbon of glucose, and carbon 2 is the anomeric carbon of fructose. So that means both the anomeric carbons of the two sugars are involved in the glycosidic linkage, and so there is no reducing end. The fructose, this is a furanoside, which again says that is also a glycosidic linkage, so it doesn't open up to become the linear structure. So both rings are permanently rings. And that's why it is mentioned that one is alpha, the other is beta, and it is between 1 and 2. 1 is the anomeric carbon of glucose, 2 is the anomeric carbon of fructose. Remember, fructose has a keto group at carbon 2. Glucose has a carbonyl group at carbon 1. So 1 is the anomeric carbon of glucose, 2 is the anomeric carbon of fructose, so there is no anomeric OH left. And so this is a non-reducing sugar. So sucrose is a non-reducing sugar, whereas the other ones are reducing sugars because they have one ring that has the anomeric OH. Yes?
Can you please read out the last one?
Read out, you cannot see that? It is beta, so it's alpha D glucopyranosyl. Then 1,2 beta D fructofuranoside. So furanose means 5-membered ring, furanose means 6-membered ring. So the glucose is a 6-membered ring, fructose is a 5-membered ring, and both are involved. The glycosidic linkage is between the two anomeric OHs, and so it doesn't have any anomeric OH left, so it is a non-reducing sugar. Now, in the process of digestion, the disaccharides are not absorbed through the intestinal walls. Remember, the whole idea of digestion is to break it down to small enough molecules so that they can be absorbed. And disaccharides are not absorbed, so they need to be digested further. So there are enzymes that break them down. So this one, for example, will be maltase, that will break down to give you 2 glucose, and then those are absorbed. In the same way, there is an enzyme called isomaltase that breaks down isomaltose. There is an enzyme called lactase that breaks down lactose, and there is an enzyme called sucrase that breaks down sucrose. So these are broken down to monosaccharides, which are then absorbed. Regarding, since you are in pharmacy, there will be certain diseases associated with deficiency of enzymes. The maltase and isomaltase really doesn't have much deficiency. There are some people who have a deficiency of sucrase, especially in the northern Alaska or northern Canada region. But very few people have a deficiency of sucrase. But a whole lot of people have a deficiency of lactase, mainly in Asia and Africa. People have a deficiency of lactase, especially as you grow older, you get less and less of lactase. So people will have a problem digesting regular milk because of the lactose in it. But now there are solutions. There are lactase enzymes or lactose-free milk available, which can solve the problem. So the problem with lactose intolerance is that anything that doesn't get digested goes into the small intestine. There also it doesn't get digested. It goes into the large intestine, and there are bacteria that will digest it. And when they digest any undigested food, not just lactase, but anything that is undigested, for example, fibers, or if you have taken too much food and there is too much of acid, and that also causes indigestion problems, so those will all be digested by the bacteria. And then in the process of digestion, it produces different gases that causes the bloating and the pain. So that's the reason for the lactose intolerance, as well as any digestion problem involving food that is not digested. All right, so I will erase all these. All right, so one thing that I mentioned before, that another polysaccharide is the peptidoglycan. So we look at starch, which of course we don't make, we make glycogen, but starch is in our food. Another related polysaccharide is the peptidoglycan. Again, we don't make it, it's bacteria make it, but because we are infected by bacteria, you need to just know some few things about the peptidoglycan. So it is a polymer of two glucose units that are modified. One is called NAM and NAM. We are not going into the structures of these, but they all have a glucosamine residue. So glucosamine means there is an amino group somewhere. One of the OH of glucose will be modified by having an amino group instead of OH, but usually it is at the C2 position. So C2 or OH is converted to NH2. That is called glucosamine. Glucosamine is very common in many biochemicals, and that glucosamine can be acetylated, so you can take the amine and form an amide linkage with acetic acid, so it forms acetyl group, and that's what this one is, N-acetylglucosamine. N-acetylmuramic acid is another derivation of the same glucose, N-acetylglucosamine, with another modification at 3. So this is a modification at 2 with the amino group at 2, and then that is acetylated. This is also same. It also has another group at position 3, which is called the muramic acid. But that's not what we are looking at. It will be linked to amino acids. 1, 2, 3, 4, 5. So it will be linked to amino acids, and these amino acids, as I mentioned before, are not the usual amino acids. Some of them are, but if one of them is the usual one, the other one is not, then the peptide bond becomes unusual. So the bacteria makes it certain that all the peptide bonds it has in the cell wall are not the natural peptide bonds. And so the host cell cannot degrade the cell wall. The host cell means the human cell will not be able to degrade the cell wall. That's why the bacteria make it on purpose with unusual peptide bonds. So in this way, every alternate, so this will keep on, this is a polymer. So every NAM will have this linkage. And then this one will have 5 glycines like this. 5. So if this is the monomer unit of the cell wall, if we draw that this way, so there is one linear chain, another linear chain, another linear chain like this, and then these peptide bonds are here with the glycines, and this one also has so this will be the structure of the monomer unit in the peptidoglycan. And there is another step that the bacteria do to make the cell wall more strong. They cross-link these chains. So this glycine comes close to this one, and it forms let's say it forms a peptide bond here. I'm drawing a long dotted line, but those are close to each other to form a peptide bond. Sorry, I have to draw this here. It goes to this one. All right, so every glycine then will form a peptide bond to this chain. And that cross-links them. Although the dotted line looks a long one, but these are next to each other, like this is one chain, this is that one chain here, so this happens to be close to this one. And forms a peptide bond there between the glycine, and the last one is G-alanine. So this linkage is called cross-linking. That's what makes the peptide bond, the peptidoglycan, strong. And the antibiotic penicillin inhibits formation of this cross-link. So it inhibits the formation of a peptide bond between the glycine and this last G-alanine. And that's how it kills the bacteria, because if the cell wall is not strong, then the bacteria will not survive. And when you do that, just look at this structure. So there is actually one more amino acid on each of these. So there are 2 D-alanine at the end, but one of them is removed after the cross-linking, and that's why I had one less. So this will have a glycine, 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 and then it links to the next one in the next chain. 1, 2, 3, 4, 5. So here is a D-alanine and a D-alanine. So when this glycine forms a bond with this one, this bond breaks and the D-alanine is released. So that is the peptidyl transferase reaction, which is forming the peptidoglycan, and penicillin inhibits this reaction because the structure of penicillin resembles the structure of dealanine, as we saw before, and penicillin is a suicide inhibitor because when this bond is formed between the glycine and the alanine, this part leaves, the dealanine leaves. If you have penicillin that looks like this substrate, so this is the substrate, the dealanine bond is the substrate for the enzyme. And penicillin structure looks like that. Penicillin is a 4-membered ring like this. It is a beta-lactam followed by a 5-membered ring, a 6-membered ring. And because it is a beta-lactam, so that means there will be a nitrogen here. And when this bond breaks, let's say this bond breaks, this is still part of the molecule because it is connected at this end. So this part cannot leave, unlike the dealanine, which is not connected to dealanine other than that peptide bond. There's only one bond connecting this to this one, so this can leave. Whereas in penicillin, there is a ring. This second ring is attached to the first ring at 2 points. So if you break one of them, it is still attached to the ring, and so it cannot leave. And if it cannot leave, then the enzyme cannot move on to the next step, and that's how it gets stuck. So that's how all suicide inhibitors work. That means it forces the enzyme to start catalyzing the reaction, and then the reaction cannot proceed anymore, so the enzyme is permanently inactivated. And so you need a 1-to-1 stoichiometric ratio. All right, so that's about the peptidoglycan. And we already talked about glycogen, which is very similar to starch, and we will also discuss more about glycogen because that's what gives you energy in the muscles. We will do that later. So before we move on to the glycolysis and other pathways involving carbohydrates, remember the whole idea of all these pathways is to get energy, to make ATP. Or what is ATP used for? It is used for other reactions that require energy. So ATP is, you can say, the energy currency. Just like you buy things with dollar, cell uses ATP for all its energy needs. So what is so special about ATP that it is always used for energy? Now, first of all, ATP is not really the only molecule that is used for energy. There are many others. Everyone gives the example of ATP, but there are several others. But why are these used for energy? So for any reaction, as you know, in the energy diagram, if this is the energy diagram of reactants and products, the amount of energy released is this much. So any reaction that releases energy can be used for other reactions that require energy, and that is decided by this release of energy. So any molecule that releases energy can be used. Now, how can you make this energy more than what it is? Anything that releases energy like this is called a high energy compound. For example, if you have ATP reacting with water, ADP plus phosphate, and this has a negative delta T, and that's why ATP is called a high energy compound, and the energy released is used for other reactions. So what factors for any reaction will make delta G more negative? That means make it a high energy compound. You can either have an unstable reactant or you can have a more stable product. So one possible way is to have an unstable reactant instead of energy here. If you have energy here, then that gives you this much of energy. So this second reaction will have more energy in it and can be used for as a high energy compound. The other way it can be a high energy compound is if it starts with the same energy but the products are more stable. So it can be something like this. This also gives you more energy. So in order to answer a question of why ATP is commonly used, we have to see why ATP is unstable and why the products ADP and phosphate are stable. So either the products must be stable or the reactant must be unstable to make something a high energy compound. So let's look at the structure of ATP. As I mentioned many times before, ATP is adenosine, ribose, and then 3 phosphates. So let me draw the 3 phosphates. And when this hydrolyzes, it gives ADP. Plus phosphate, 3 phosphate. Alright, so this is the reaction of hydrolysis of ATP. ATP has 4 negative charges. Anything that has more negative, any charges on it makes it unstable. Nature doesn't like charge. Anything that is charged is unstable. So ATP has more charges than the products. This one has 3, this one has 2, this one has 4. So 4 charges means more unstable. So we are answering the question, what makes the reactant unstable and what makes the product stable. So one factor is the number of charges. There are more charges on one molecule on the left side, and that's why the reactant energy is high. The other factors have to do with the product. What makes the product more stable? And you studied in organic chemistry that if you can draw resonance structures, that makes it more stable. So let's look at the phosphate here. This negative charge can be shared by this oxygen. So you draw an arrow here and this electron goes to the oxygen. So there is equal charge on the 2 oxygens. Same thing with this. There will be 2 resonance structures. For the terminal phosphate, so these are internal phosphate, this is the terminal phosphate, there will be 3 resonance structures because there are 3 oxygens sharing the charges. So you can have the charges, 2 negative charges on these 2, or these 2, or these 2. So there are 3 possible resonance structures. So the internal phosphates have 2 resonance structures, terminal phosphate has 3. So anytime you have more terminal phosphates, that will have a greater resonance stabilization. So how many terminal phosphates on the left side? There is only 1. So 1 terminal phosphate, and this one has 1 and 1, 2. So 2 terminal phosphates. And more terminal phosphates you have, more resonance structure it will be, and that makes it more stable. So this is stabilized by resonance. More stable by resonance. And that's what you want. You want the product to be more stable, and in this case the products are stable because there are more terminal phosphate, that means there are more resonance structures. There is another way the charges can be stabilized, which you studied before, like you take sodium chloride to dissolve in water. Why does it dissolve? Because the ions are surrounded by water, and that stabilizes the negative and positive charges. That stabilization is called the heat of hydration or heat of solvation. So energy is released when ions are stabilized by the solvent, and that's called the energy of hydration. And more the charge density, more will be the energy of hydration. So here you have charges on a bigger molecule compared to charges on a smaller molecule. And here you have two charges on a very small ion, which is the phosphate. So on this side there is more charge density. And more charge density means more energy of hydration. And that makes the product more stable. So the product is stable because of resonance and hydration. The reactant is unstable because of too many charges. And that's what makes ATP a so-called high energy compound. So once again, what is a high energy compound? That is related to a hydrolysis reaction. Any compound that is hydrolyzed and releases a lot of energy is called a high energy compound. So that is the definition. It doesn't mean that the molecule is actually hydrolyzed. For example, if I have a pen at a high altitude, it has potential energy. How do you know that? Because if it falls on the ground, it will release the energy. But that doesn't mean this is always falling on the ground. In fact, if it does fall on the ground, it will not have that energy anymore. That energy will be released as heat energy. So it is a measure of energy that we are saying this as potential energy. In the same way, this is the energy that is in the molecule. Doesn't mean that it will be actually hydrolyzed. In fact, they are rarely hydrolyzed in the cell. But if it is hydrolyzed, this will release a lot of energy, and that's why it is called a high energy compound. But in reality, they are rarely hydrolyzed because just like the pen falling on the floor, it doesn't have the energy anymore. So if it is hydrolyzed, that energy is lost as heat energy, which you don't want. The body temperature is constant, and that depends on the various amounts of energy that are released in so many reactions. If you have any reactions releasing more energy, that increases the body temperature. So we don't want to hydrolyze any high energy compound without using that energy for other reasons. Alright, so besides ATP, there are other high energy compounds also, and for each of them there will be a different reason for why they are high energy compound, and it always has to do with the reactant must be unstable, the product must be stable, or a combination of the two that will make them high energy compounds. So I send you a list of various high energy compounds in the email, and for each of them there will be a reason why it is a high energy compound. We will not go over all of them, but the one that is at the top of the list is not ATP. So ATP actually gives you about minus 32 kilojoules per mole. There are molecules above ATP also that give you even more energy. At the top of the list is this molecule called phosphoenol pyruvate, which is minus 60 or something. Phosphoenol pyruvate is one of the highest energy compounds in the cell, and so it can also be used to do any reaction that requires energy. In fact, phosphoenol pyruvate is used to make ATP. So what is the reason why phosphoenol pyruvate is a high energy compound? The reason for this is different from ATP, but the concept is still the same. Either the reactant will be unstable or the product will be more stable. So the name phosphoenol pyruvate. So the term enol you have studied in organic chemistry. And if you don't remember, you should go and study that again, because that's important. That's what makes this a high energy compound. So all ketones, for example acetone, is in equilibrium with the enol form. That means you put a OH here and the double bond comes here. So this is the keto form, this is the enol form, and they are always in equilibrium. All ketones are in equilibrium with the enol, and this is called the keto-enol tautomerism. And these are called the tautomers. So all ketones are in equilibrium with the enol, and of which the enol is usually more unstable, and that's why I have the equilibrium more towards the ketone. So the point here is that the enols are unstable, usually unstable. Sometimes the enol is actually more stable, like phenol. Phenol is more stable than the corresponding ketone because of the aromatic ring. But usually the enol is more unstable, and this molecule, phosphoenol pyruvate, so here is pyruvate. And this will also exist as the enol. So once again, it's mostly as the ketone. So this is enol pyruvate. So enol is more unstable, so most of the molecules are in the keto form. But then in the phosphoenol pyruvate, this OH forms an ester linkage with phosphate. And so phosphoenol pyruvate is this molecule. Phosphoenol pyruvate, and what this does is this prevents the enol to convert to the ketone. So this will not convert to the ketone because of the phosphate. The reason enols convert to the ketone is because this is a OH, and you have studied in organic chemistry, it accepts a proton from water, so it's all in water, and in water it will equilibrate. But if it is a phosphate, that locks it into the enol form and does not let it go to the keto form. And that's what makes it a high energy compound, because it is permanently in the higher energy form as the enol form. And that is actually the highest in the list of high energy compounds. What will happen again, high energy compounds are defined in terms of hydrolysis reaction. So if this is hydrolyzed, so there will be an enzyme that will, this is not an equilibrium reaction, this is a separate reaction that will remove the phosphate by adding water. In biochemistry, you will often find these reactants and products written on the arrow itself. You already know if there is a reactant on the arrow, you can write it this way, or if it is a product, you can write an arrow coming out of an arrow, and that is the product. So it's a very frequently written way of short form of reactions. So if you add water and remove the phosphate, then this becomes the enol, and enol immediately equilibrates to the ketone. And that's how it releases a lot of energy. So as soon as you remove this phosphate, it goes in this direction, which is more stable, and that releases this much of energy. And that's why phosphoenol pyruvate is a high energy compound. One word of caution for people who are more knowledgeable in chemistry. You know that in chemistry there is another term called a high energy bond, which is a totally different concept. It is energy for breaking a bond, whereas this is a hydrolysis reaction. So don't confuse between a high energy bond and a high energy compound, which is used by biologists. high energy bond is used by chemists for a particular bond. Here it is the compound itself that is high energy. Alright, so these are high energy compounds. There is another molecule that we need to talk about why it is a high energy compound. So I will erase this. And those are the thioesters. And the thiol group you will find in a coenzyme called coenzyme A. Coenzyme A is also written as CoA. Coenzyme A is a relatively large molecule. We won't go into the structure, but it has adenosine, then ribose, and the ribose has an extra phosphate also, and then another phosphate and another phosphate. So basically it is ADP with one another phosphate, and then there it is attached to a pantothenic acid. The structure of it is given in the book, you don't have to know. Pantothenic acid is a vitamin. You have never heard of that vitamin, but it is a vitamin. So pantothenic acid is a vitamin that is attached to a ethanol amine, and that is attached to a SH group. So all this is something important, but of course not so important. What is important is this SH group. And for that reason, this is also written coenzyme A. Instead of drawing this whole structure, people write it as CoASH. So CoASH to emphasize that it has a SH group at the end. So it's a sulfhydryl group at the end, which is the main part of this molecule, and that is what is responsible for all its reactions. So instead of remembering the whole structure, you can just remember CoASH. But the reason I drew this structure is to emphasize another point, that this molecule is highly charged. This is a phosphate that has two negative charges. Sorry, this will have three negative charges, or two depending on whether it has a H or not. Then this has negative charges on them, one each. So that makes it, let's say 2 plus 2, 4 negative charges. And why am I bringing that up? Because anything that is charged cannot go through the membrane. So we will see later that coenzyme A cannot cross the membrane. That is true for anything that is charged. ATP cannot cross the membrane. Anything that has charges cannot cross the membrane. So in order to go through the membrane, it needs a transporter. Anything that is charged will go through the membrane using a transporter or using another molecule. Instead of coenzyme A actually never crosses a membrane. It transfers whatever it is supposed to transfer to some other molecule, and that takes it inside the membrane. So just remember that it has charges on it, and we will need that information later. But for now, it is just a large molecule with a SH group at the end. And this is a thioester, so SH group is actually not present as SH, but it is an ester linkage. So thioester will be something like this. So coenzyme A, the SH forms a ester linkage with the acetyl group, and that makes it thioester. And thioesters are high energy compound because the reactant itself is unstable. Once again, remember, either the reactant must be unstable or the product must be more stable, or both. And thioesters are unstable compared to the oxoester. So let's draw a regular oxoester. So this is an oxoester, not a sulfur, but oxygen. And as you know, there are 2 electrons here. So you have a resonance structure. These electrons go here. These electrons go here. So that gives you a resonance structure. Right. So all oxoesters have resonance structure, and resonance makes it more stable. So that's why oxoester or regular esters, as you know, are more stable than thioesters. Now, sulfur is in the same group as oxygen, so it also has these 2 pairs of electrons. So you can draw a resonance structure like this. Right, so you can draw a resonance structure like this, but actually this doesn't happen. So oxoesters, resonance happens, makes it more stable than thioesters, in which the resonance does not happen. Why does the resonance not happen in thioester, or happens very poorly? This again you have studied in organic chemistry, that in order to form a double bond, how is a double bond formed? You have carbon and the oxygen. That forms a sigma bond, and there is a p orbital and a p orbital with 2 electrons, and they overlap to form the pi bond. This kind of overlap can happen if the 2 p orbitals are of similar size. If they are not of similar size, then you don't get a good overlap. So if you are looking at this one between carbon and sulfur, so here is the carbon p orbital, and here is the sulfur p orbital, because sulfur is in the next period of the periodic table. It has a larger p orbital. And so this overlap is not efficient overlap. So you don't get a pi bond formed so easily, so that's why this resonance structure doesn't happen, because the 2 p orbitals are of different sizes. And that's what makes thioesters high energy compounds, because of lack of resonance. And so thioesters are used as high energy compounds in many reactions. We will study a lot of that in lipid metabolism, where all the energy you get from lipids come from these thioester linkages. Alright, so that's how all these high energy compounds work. The others also in the list, I'm not going to all of them. So these 3 you need to know, ATP, PEP, and the thioesters. And with that, we will start glycolysis, and as you wanted, a few minutes break. We will move on to glycolysis after
I can't take myself. You understood the lecture? Of course not, right?
Yo, did it get me holding my iPad up to take pictures?
Mark, you're not allowed to make decisions. Mark, I mean, it's in 40 pounds. Mark, I can't. I'm a lot bigger than that. Look at that. See how easy that was? Yeah.
He lubed it up.
whoever has the attendance sheet, please return that. Let's see if people have signed. No, but it's a reaction with water. It's a reaction. A high energy bond is breaking a bond using some high energy particles. So you're not having another reactant, it's just a source of energy. We can say light or X-ray or something like that. Some high energy fact that breaks the bond. There is no other reaction. No other reaction in deciding high energy bond. Alright? So high energy bond is mainly required to break a bond. Whereas here you are actually forming a bond with the bond. So you have this reaction. And two are not at all related. Just that coincidence that the biologists have used different similar characteristics for a different meaning. So not to get confused.
And then what am I gonna
So they have no connection with each other.
You mean in patho too? Oh, do we?
I mean, I don't know what you're doing, but she was like, so I mean, decided for directing my brother, my drafting a message to his teacher on He was drafting the message like on the app itself, and my brother told me, and the message said, no way. And it read, hi, this is Maddie's dad. He's bad at home. And before we could even click sorry for the inconvenience, the teacher replied back, that's surprising because he's a Ron Law student. No, we have to wait so sorry for the new super little grade. So you can now because they like boarding again. She was probably like, yeah, like at home, something at school. But she was really sweet about
Huh? No, it's melted. Don't worry. It makes you proud. It's I already finished. What else do you do to complete the slides? Read the slides, watch the videos. That was something. And read the articles. There's 3 articles you have to know. One of the articles is about and what is it? NPIM. Case study. You just need to know the social hygiene theory. It's like you literally do not know it. The article does not make sense when
I low-key don't want to sit yet, just because I want to keep it. No, wait. Hey, move. I want to sit. No, I need to keep my legs stretched. I'm Mark. We doing this again, Mark?
What's up? No, you got it.
Nah, this is unacceptable.
because I'm gonna be the you're no longer.
I get it. My leg got a stretcher.
Listen, I said like that shit a long time ago.
Cultural value.
I didn't take it.
Huh?
I don't remember any.
All right, safe. All right.
God, he started.
Oh my god, I'm gonna miss
Sorry.
Are you laughing?
Biochemistry is no one ever said biochemistry is hard.
I got a long So happy.
Alright, looks like people are back. People want to come back. One more thing before we go to the next topic. These numbers in the list. I said I gave you a list of all the high energy compounds. It's also in any book. If you look at the top of that table, these numbers are delta G0 prime. All right. Now, what is this G0? You already know from various general chemistry classes. Delta G0 is the standard free energy. So the actual free energy, delta G. The actual free energy of any reaction is decided by the standard free energy plus the ratio of the reactants and products and reactants, right? So it's not always the same delta G value for all conditions. It depends on the concentration of the reactants and products. So this is a term that you have seen before. This is called the standard free energy, and this is what is listed in any table. If you look in the chemistry book, it will be called delta G0. In the biochemistry book, it is a delta G0 prime. And they are not the same thing. So what is the prime thing doing here? In biochemistry, as you know, all reactions happen in water, right? They are all water-based. Whereas if we use the standard free energy, it can be acid, it can be pH 7, pH 1, pH anything. So what happens is, if you have a constant pH, the concentration of the acid figures into either the product or the reactant every time. Like 10 to the minus 7, log of 10 to the minus 7 is 7. So you always have to keep adding that 7 to this constant, because water has a pH of 7 always, and that is a constant. So why not bring that constant over into this standard free energy? So any reaction that has either acid or base as a reactant or a product, you will see a difference between delta G0 and delta G0 prime, because the log of that pH, log of that acid concentration, which means the pH, is incorporated into the delta G0 standard. And that's why we always use the delta G0 prime. And this also tells us that whatever this number is, that is not written in stone, because this is the standard free energy, and those conditions are never present in the cell, right? The cell will have a certain concentration of the reactant and the product, and delta G will change. Now, as I mentioned before, all metabolites are usually kept at a constant concentration, except for those that are used more frequently, or those that are coming from outside, like from the food. One thing that is used more frequently are these high energy compounds, like ATP. Whenever you need ATP, ATP is broken down and so ADP concentration increases. And when you are not doing exercise, then the ATP concentration increases. So these cannot be at a fixed concentration. They are fixed when you are at rest, but other times they are fluctuating. And so the actual delta G, whether the reaction will happen or not, which direction the reaction will go, all that is decided by this overall delta G and not by the delta G0 prime. One example of that discrepancy you will find is this high energy compound called creatine phosphate. Creatine phosphate, people may have heard of creatine, right? So creatine phosphate has in the list, it is listed as minus 43 kilojoule per mole. That means it is a higher energy compound than phosphate. Anything that is a higher energy, ignore the negative sign, they are all negative. So if the number is higher, that means it is able to transfer a phosphate to one that is lower to make that compound. For example, a phosphoenol pyruvate is a higher energy compound than ATP. So phosphoenol pyruvate is used to make ATP. So phosphoenol pyruvate will make ATP from ADP and phosphate. So anything that is higher in the list will be used to make the one lower in the list. For example, ATP is minus 32 and then glucose phosphate is somewhere around maybe 15 or 20. So that's why ATP is used to put a phosphate on glucose, because glucose phosphate is a lower energy compound than ATP. So same way the creatine phosphate, if you don't know what it is stored in the muscles for emergency source of ATP. So when you are doing exercise and all your ATP is used up, then you can get ATP from creatine phosphate that is stored in the muscles, and that will transfer its phosphate to ADP to make ATP, because this is minus 43, this is minus 32. Then what happens to all that creatine phosphate that now becomes creatine? If it transfers the phosphate, it becomes creatine. And then what will happen to that creatine? It must get back its phosphate from somewhere, because it is a stored thing, just like the myoglobin is stored in the muscles, and it must get back its oxygen if it has to release the oxygen. So creatine phosphate will get back its energy from ATP. So ATP plus creatine gives creatine phosphate plus ATP. So both reactions happen. You can have creatine phosphate transferring its phosphate to ADP to make ATP, or creatine can react with ATP to make ADP. Which direction will the reaction go? That depends on which one is present in more amount. Remember, the creatine phosphate in the muscles, and that will be used to make ATP only when you don't have ATP. Right? If you have ATP, then the stored creatine phosphate will not do anything. So if you don't have ATP, that means you have a lot of ADP. All your ATP is used up. So this side is now higher in amount, and that's why the reaction goes in this direction. When you have used up all your creatine phosphate, they are all converted to creatine. You don't have any creatine phosphate left. But you are making ATP, that means at rest, not while you are doing exercise. After the exercise, you have made enough ATP, so your ATP concentration increases, and that will be able to transfer phosphate to creatine to make that creatine phosphate again. So all these numbers are not fixed. They are the standard free energy. The actual free energy will depend on the concentration of the reactants and products. So the reaction can go either way. Sometimes ATP can be used to make creatine phosphate, other times creatine phosphate can be used to make ATP, depending on how much of the reactants and products you have. Alright, so we will move on to the first metabolic pathway, which is glycolysis. So glucose is converted to pyruvate through 10 steps in the metabolic pathway. As we saw before, all metabolic pathways have multiple steps. This one has 10 steps. And if you follow the delta G0 of these, so it will look like this. So in the 10 steps, so in step 1, it's like this, then like this. So this will be the energy. So delta G0 prime versus reaction number. So there are 10 reactions in this pathway. So for each of these reactions, this is the delta G0 prime. Now this doesn't look like the rules that I mentioned about all pathways, because all pathways must move forward. That means all of them must have a negative delta G. You cannot have a positive delta G. So here are several reactions where you are having a positive delta G is increasing. It's increasing here. That is not allowed for any pathway. And this is happening because you are plotting the wrong thing. You're not supposed to plot the standard free energy, you're supposed to plot the actual free energy, the delta G, and not the delta G0, because the actual delta G depends on the amounts of the concentrations of the reactants and products. So those have to be taken into consideration, and you have to actually plot the delta G values. And if you do that, instead of delta G0, it's delta G, and then it looks like this. So, as I said, in a pathway you have two types of reactions. They are either irreversible or close to equilibrium. No reaction is at equilibrium, but they are close to equilibrium. That means these reactions, this one and all these other ones, they have slightly negative delta G. It's never positive, it's never zero. It is always going down, but slightly. And those that are going down a lot, those are called the metabolically irreversible reactions, and others are metabolically equilibrium reactions or near equilibrium reactions. Because as I mentioned before, whether it will be irreversible or equilibrium depends on the actual concentration of the metabolites, and the cell maintains the concentration such that all pathways must move forward. That means they must have a delta G that is negative. So the overall pathway has a delta G, this minus this, which is negative. That is the property of any pathway. It must have an overall negative delta G. Not only that, every reaction in the pathway must have a negative delta G, either slightly or highly. So there are 3 irreversible steps. This is step number 1, step number 3, and step number 10. So first, third, and the 10th step in glycolysis are irreversible. And you need to know what these reactions are. So if I ask you which steps are irreversible and you write 1, 3, and 10, that's not the answer. Right? So you need to know what steps these are, and we will go over that. So of course it starts with glucose. So glucose will enter the cell from the blood, comes from the diet, or from stored glucose as glycogen. And once it enters the cell, then it will add a phosphate to the carbon 6. So this is glucose, and this is glucose 6-phosphate. So once again, I have mentioned this many times, anytime I write a P with a circle, it means it has 4 oxygens on it. So of course this will require ATP, and as I mentioned before, reactants are often shown on the arrow. So you can show it this way, ATP gets converted to ADP. And of course, all reactions are catalyzed by an enzyme, and this enzyme is called hexokinase. As I mentioned before, all enzymes that transfer a phosphate is called a kinase. So this is a hexokinase, which means it transfers to the 6-carbon sugar, or hexose. Now this serves two purposes. Remember I mentioned molecules don't just cross the membrane. Anything that is polar, charged, they don't cross the membrane, they must have a transporter. So there is a transporter for glucose. So all cells will have the glucose transporter on the membrane that will take the glucose in. And the whole idea about insulin and all these diabetes, people suffering from diabetes, that has to do with insulin and the transporter. You may have insulin, but you may not have the proper transporter, and then the glucose doesn't go into the cell. So blood glucose stays high, or you may not be making enough insulin, so then also the blood glucose remains high. But the point is, every molecule must go through a transporter, except very small molecules like gases, which don't need a transporter. Or some of the hydrophobic molecules, like some of the hormones that are hydrophobic, they also don't need a transporter. But other than that, most molecules need a transporter, so glucose will go through the transporter into the cell, and if it goes in, then it can go out also, right? You don't want that. The cell doesn't allow things to just go both ways unnecessarily. The purpose is to bring the glucose in, so it doesn't want it to go out. And so what it does, it puts a phosphate on it. And the phosphate is negatively charged, so the phosphate cannot cross the membrane. And not only that, any transporter that is meant to transport glucose will not transport anything else. So it will not transport glucose phosphate. It may not be phosphate, it may be any other molecule. All transporters are very specific. So a glucose transporter will only transport glucose, it will not transport if glucose is modified to something else. So this serves two purposes, that it is modified or with a phosphate that has a charge, so it cannot just go by itself, or it cannot even go through the glucose transporter. Secondly, the ATP that is used here, as I mentioned before, ATP is never hydrolyzed, right? If it is hydrolyzed, that energy will be lost. So the phosphate, the gamma phosphate of ATP, remember ATP has 3 phosphates, alpha, beta, and gamma. The last one is a gamma phosphate. That gamma phosphate is transferred to glucose, and in the list of high energy compounds, ATP is 32, glucose phosphate is something like 15, 16, so that's why it transfers the phosphate to glucose. But the energy is still there in the phosphate bond. It will be used later to make ATP. So we are not really wasting energy there, but storing it in this phosphate bond. So hexokinase, there are 4 enzymes. And if there are 4 enzymes, what will they be named? 1, 2, 3, and 4. So these are called hexokinase 1, hexokinase 2, hexokinase 3, and hexokinase 4. The hexokinases 1, 2, 3, and 4. The number 4 is also called a glucokinase. Anytime you have more than one enzyme doing the same reaction, why do you need more than one enzyme doing the same reaction? But there are some of them. When that happens, those are called isozymes. So 4 hexokinases will be called isozymes. And for all enzymes, you won't find isozymes. You will find isozymes for only some enzymes. And what is special about these enzymes? They are dealing with a substrate whose concentration varies tremendously. As I said, the cell maintains the concentration of everything to a certain level. And if that happens, you don't need more than one enzyme, you need one enzyme. So for most metabolites, you need one enzyme, you don't need 2 or 3. For hexokinase, there are 4 of them because the concentration of glucose can vary a lot depending on how much food you're eating or how much carbohydrates you're eating. And in those cases, you need more than one enzyme. Why you need more than one enzyme? What is different about these enzymes? They are different in the Km values. Going back to the chapter on enzymes, if you remember, this is the Michaelis-Menten diagram. And let's say you have this is the hexokinase and glucose enzyme. If the Km is here, so this is the Km. Let's say the Km is a certain micromolar. So these 3 have Km in micromolar range. That means between 5 to maybe a couple of hundred micromolar. So because the glucose concentration varies a lot, you need an enzyme that will be active at very low glucose, and you need an enzyme that will be active at very high glucose. If you had only one enzyme that had a Km of, let's say, 5 micromolar, how much is the actual concentration of glucose in the blood? Anyone knows? Or pharmacists, you are going to deal with all these blood reports. Anyone read a blood report of any glucose concentration? What is the normal rate? Normal blood glucose concentration? It's how much? 100. Okay, what 100? A number without a unit is not a number. What is the unit? 100 milligrams per deciliter. Yes, where is the deciliter coming from? Pharmacists, nurses, doctors, they like deciliters. They don't like the liters. Things are mentioned in deciliter all the time, which is 1/10 of a liter. Right? So as pharmacists, you should know this term deciliter because all the concentrations are mentioned as grams per deciliter or milligrams per deciliter. So it is 100 milligrams per deciliter is the normal glucose concentration. If you convert that to liter and then to convert to moles, that will come to about 5 millimolar. So a normal glucose concentration is about 5 millimolar. Alright, so those who are transferring from chemistry to pharmacy, you should know that you knew it as 5 millimolar, now you will know it as 100 milligrams per deciliter. So anyway, that is 5 millimolar. So the Km is in the micromolar range, maybe one of them may have 1 millimolar or 0.1 millimolar. What will happen if your concentration in this range? You need 10 times this and the rate doesn't increase that much. It only increases to twice the Km value, right? You can increase the concentration 10 times and the rate increases only by 2 times. So this enzyme that works very well at a very low concentration of glucose, you need an enzyme to deal with low concentration, will not work at all at very high concentration because it is fully saturated. And when your blood glucose level right after that high carb food that you ate can go up to 30-40 millimolar. Right? That's a very high, and that will cause a lot of problem. You need to bring that down very quickly. How do you bring it down quickly? You need hexokinase to do that. And hexokinase cannot really function if this is the Km. So you need a hexokinase with a high Km. So the glucokinase has a Km of about 10 millimolar. So if you have isozymes, most likely, not always, but most likely they have different Km values dealing with different concentrations of glucose. So when the blood glucose level is very high, right after a meal, it is the glucokinase or the hexokinase 4 that deals with it. And that is never saturated because it has a 10 millimolar. To be saturated, the blood glucose needs to be 100 millimolar, which you should never have. If you have, you really have a big problem. Alright, so this enzyme never gets saturated, so that's why you have this enzyme with a high Km, and you need an enzyme with a low Km because the blood glucose level can be at a low level also. Inside the cell it is much lower than 5 millimolar. 5 millimolar is in the blood, but when it goes into the cell it is much lower, so you need an enzyme for that concentration also. Alright, so in the second step of this glycolysis reaction, which you put another this is converted to fructose, and so you are converting the glucose to a fructose. So whenever you are doing that, that will be an isomerase enzyme. That means you are changing the position of the OH group. So if we look at the linear structure of this CHO, 1, 2, 3, 4, 5, 6. And remember the structure of glucose is right, left, right. So, and this has a phosphate here. So once again, remember the first step is irreversible, and then the third and the 10th are irreversible. The others are equilibrium steps. So that means this is an equilibrium step in which you are moving the OH from here to here. So if you draw the keto group like this, aldehyde. So this keto group will come to this position and the CH2OH goes here. Whenever that happens, it usually goes through an enol intermediate. Anytime you are moving the OH from C2 to C1 or C1 to C2 or just the next carbon, you form an enol here and then again a ketone here. So this will go through the enol intermediate like this. Alright, so all ketones are in equilibrium with the enol, and then again this becomes a ketone. Because there are two OH groups, there's OH here and the OH here. So either of them can become the carbonyl group. So if this becomes a carbonyl group, you get back the glucose. If this becomes a carbonyl group, you get fructose. So this will be the fructose. So fructose 6-phosphate. And the name of the enzyme will be based on what it does. It takes phosphoglucose and isomerizes it. So it's called phosphoglucose isomerase. Whenever you look at any pathway and see why there are so many steps, we saw the reason regarding energy and other factors. But here there is no such factor here, there is no energy involved here. But there is always a reason why the cell wants to convert the glucose to the fructose. what does it gain by doing that? And to understand that, we have to look at the whole pathway, what is happening after this. So after this, there's an enzyme that will put another phosphate on it. Another ATP, and that puts a phosphate on this one. So this was fructose 6-phosphate, and this is fructose 1,6-bis phosphate. I mentioned before the difference between di and bis, like ADP. The di means 2, the bis also means 2. The di applies to 2 phosphates one after another. That means one phosphate is linked to another phosphate, and the bis phosphate means the 2 phosphates are 2 separate carbons. So that's why this is a bis phosphate, for phosphate at 1 and phosphate at 6. And obviously it will need energy to put a phosphate, and so ATP is used for that. And this is the third step, and the third step is the irreversible step. So remember, for step 1, 3, and 10 are irreversible. And the name of the enzyme, because it is putting a phosphate, it will be a kinase, and it is putting a phosphate on fructose phosphate. So it is called phosphofructokinase. When we did the metabolic pathways, we saw that pathways have reversible and irreversible steps. They are regulated at the irreversible steps, and there is always a first committed step in every pathway. So if you have step 1, so this is irreversible, then this is reversible, and then this is irreversible. So this is the phosphofructokinase. So there are 2 irreversible steps in the beginning. Which one is the committed step? 3, not 1. So what is the first committed step? It is the first irreversible step after the last branch in there. So here, this product 2 is glucose 6-phosphate. And glucose 6-phosphate is an intermediate for numerous reactions. So this participates in other reactions also. Not just one branch, there will be more than one branch starting from glucose 6-phosphate. So the first enzyme is not the first committed step, it is the third one that is the first committed step. And one thing you can expect from the first committed step is that it will be highly regulated, because that's what decides whether glycolysis will happen or not. If the cell needs energy, then only glycolysis will happen. If not, it will not happen. So what decides that? Regulation of this enzyme. So this is the enzyme that is highly regulated by the various methods we saw, mostly by allosteric regulation, that means feedback inhibition. So for example, ATP is a end product of this, so ATP will inhibit that step. Or other products from the citric acid cycle will also inhibit this step. So this step is highly regulated. The first one is an irreversible step, so hexokinase is also regulated to some extent, but not as much as this. but this is the most regulated step in the whole pathway. So as I mentioned, every reaction has a reason. Yes? The one that is regulated, so the third one is the first committed step. Third one, which is fructose phosphate to fructose bisphosphate.
Right. That's right.
That's the one that is highly regulated. All the reversible steps are regulated to some extent, but this one is the one that decides whether glycolysis will take place or not. So this must be turned on and off very strictly, right? And it will be mostly by allosteric regulation, which is feedback inhibition. All right, so the question is, why did glucose convert to fructose, and why are you putting another phosphate on it? So instead of making energy, we are actually investing energy into the pathway. Remember, the whole function of a pathway is to give you energy, give you ATP. But till now, we have already invested 2 ATPs in the first step and in the third step. So up to the steps 1 through 6, out of the 10 steps, in steps 1 to 3 and 1 to 6, you are not really making any ATP at all. That's the whole idea of glycolysis, is to make ATP, but you are not making any ATP. Instead, you actually invested ATP into that. So these are called the energy investment phase. And in the energy investment phase, you have used 2 ATPs in the 2 steps. And then in steps 7 through 10, we will actually be making ATP. So that will be the energy generation phase. And you will be making 4 ATPs. So this is minus, this is plus, so you are making net 2 ATP for glucose. So the whole of glycolysis gives you only 2 ATP per glucose. If you put that in perspective, is the total amount of ATP you get from one glucose molecule is 32. So out of that 32, you have made only 2 ATP in glycolysis, and the remaining will be made later. So glycolysis doesn't really give you a lot of energy, it gives you only 2 ATP. But then there are some organisms that rely entirely on glycolysis for all their energy needs. That means it has to carry out glycolysis at a fast rate repeatedly, because this is the only energy they have. They don't have any other form of energy. So all these steps, as we will see, we have done only the first 3. There is no oxygen involved. So glycolysis is an anaerobic pathway. As opposed to the next pathways, which are aerobic pathway, which means they involve oxygen. As we will see later, they don't really involve oxygen directly in their reactions, but they depend on oxygen, not oxygen is involved in the reaction. But glycolysis doesn't depend on oxygen at all. It can happen in the absence of oxygen, and so that is anaerobic, and so glycolysis is also called a fermentation process. Fermentation means metabolism in absence of oxygen. So in glycolysis, in the first 6 steps, you are actually investing energy, and that energy will not go into waste. As I said, you are forming a bond with that energy, and that bond will later be used to make energy, and eventually you make 4 ATPs. So that gives you a net 2 ATP for each glucose. Now, in order to get to pyruvate, Remember, pyruvate has 3 carbons, glucose has 6 carbons, so at some point you need to break it into half. Right? So when you break it into half, you break it into 2 pieces. What kind of pieces you want? Do you want a 2 and a 4, or do you want a 3 and a 3? 1 and 5? How do you want to break it into? You want 2 3s. Why do you want 2 3s and not a 2 and a 4? So let's say a C6 is broken down to C2 and C4, which it doesn't happen. What happens is it breaks down to a C3 and C3. If it did break down to C2 and C4, you must have a pathway to deal with the C2 and another pathway to deal with the C4. So you need 2 pathways to get to the end product. So the cell has to design 2 pathways, that means a whole set of enzymes for that. So that's a burden on the cell to have so many enzymes and pathways. Instead, if you have a C3, you need only 1 pathway to go to get to pyruvate. So that's why the cell breaks it. All cells, all organisms carry out glycolysis, and they will divide it into 2 pieces each, C3, so that you need only 1 set of enzymes to get to the final product instead of 2 sets. And when you get to 2 of these, you need both of them to be the same, right? Then only you can have 1 set of pathway. Remember, pathway enzymes are very specific. You cannot just have C3 and expect that the same enzyme will continue with that. So it must be the same molecule. In order to be the same molecule, if one of them has a phosphate here, the other one must also have a phosphate here, because you are breaking it into half. So they should both have a phosphate. And that's the reason why you are putting a second phosphate here. So you have phosphate here and a phosphate here, and then you cut it into half. So you have a 3 carbon with the phosphate and 3 carbon with the phosphate. Alright, so the second phosphate is added so that you get a symmetrical 2-phosphate compound, so that when you break it into 2 pieces, each of them will have a phosphate, and then there will be only 1 pathway dealing with that. So in the next step, you are basically breaking it here. So the requirement, so this enzyme called aldolase will break it into 2 pieces, and the 2 pieces will be these. And the remaining 3 will be this one. So this is a aldolase reaction that breaks it into 2 equal parts. They are still not the same molecule. What are the names of the 2? This one we have already seen before. This is a 3-carbon compound with an aldehyde on top, so that is glyceraldehyde. And it has a phosphate at the end, so this is glyceraldehyde. Phosphate, or written as G3. Just to not get confused, it's glyceraldehyde 3-phosphate. And what is the name of the first one? Remember, this is a derivative of acetone, C double bond O, CH3, CH3. Instead, there are 2 OH groups. One of them has a phosphate. So this is a dihydroxy acetone phosphate. which is abbreviated as GAT. So the enzyme aldolase breaks it up into two pieces. Each piece has a phosphate, and that's why the second phosphate was actually put in there, investing in another ATP. Now this aldolase reaction has a requirement, and the requirement is that there has to be a carbonyl group followed by two carbons with OH. And that's when it can break right in the middle of that two OH groups. If you look at the structure of glucose, that also has the same thing. So here is glucose. It has a carbonyl group, OH, and another OH. So it can cut here. The nature can make an aldolase to cut it here, but it did not do that. Right? Why? Because if it cuts there, then you get this situation, you get a C2 and a C4, which you don't want because they are different compounds and there is no way you can have the same enzymes to deal with them. So that's the reason for the second step where glucose is converted to fructose. As I said, why is glucose converted to fructose? And this is the reason that you don't want the carbonyl group at carbon 1, you want it at carbon 2 so that you can cut it into two equal halves. So the reason for the second step is to make a molecule that can be cut into two halves that are both 3 carbon compounds. And as I said, the two things are not the same, they are different. But you want only one set of enzymes after this, not two sets. That means this must be converted to this one. So these are actually in equilibrium. The glyceraldehyde 3-phosphate and the dihydroxyacetone phosphate. They are in equilibrium. And the name of the enzyme is, this enzyme is triose. It's a 3-carbon sugar, so that's why it's called a triose phosphate isomerase. That converts the dihydroxyacetone phosphate to the glyceraldehyde 3-phosphate. So these are the 6 steps that are the energy investment phase, and the remaining steps have to continue from this molecule, which is glyceraldehyde 3-phosphate. You don't need a separate enzyme for this one, the dihydroxyacetone phosphate, because that is converted to the glyceraldehyde 3-phosphate. This enzyme, triose phosphate isomerase, is a diffusion controlled enzyme. As I mentioned before, diffusion controlled enzymes are those that have very high rate of reaction, and they are usually there for toxic products. This is not a toxic product, but still this enzyme has evolved to be one of the fastest enzymes. And there is a reason behind that, because if you don't convert all of this immediately to this one, then glycolysis cannot deal with it, because glycolysis has to work with this product. It cannot deal with this product. There is no enzyme to deal with that. So if this accumulates, then the pathway will go in the reverse direction. Step 1, 2, 3, these will all go in the reverse direction because you are accumulating a lot of products. And that will go against all the rules about pathways. Remember, pathways must go forward, they cannot go backwards. And so if this accumulates, the pathway will actually go backwards, and that's why nature has evolved to not have dihydroxyacetone phosphate to any significant level. So as soon as it is formed, it is converted to this, and then the rest of the 4 steps happen quickly. All right, so we will stop here. Next class, then we will look at, yes. What